So we have seen the two modes in the previous session, namely common base mode and common emitter mode of an NPN transistor. All our study will be, as earlier I told, will be based only on NPN transistor, whether it is an application or study of characteristics or study of the structure for the various modes. We are only going to discuss only NPN transistor. Now for the collector, common collector, it is very rarely used and it does not find very wide applications. Anyway, it is included in the syllabus for your CBSE standard 12. Therefore, I will just give you the circuit. But even while drawing the circuit, you remember that emitter should be forward biased and the common terminal of collector should be grounded, and emitter should be forward biased, and collector should be reverse biased. Yes, so the circuit will go like this, because the emitter has to be the common terminal. You draw like this, and the collector is here and the emitter is here and the base is here, and it is an NPN transistor, N for emitter, P for base and N for collector. Now we pass on to how we apply the biasing, so that first us you easily remember the circuit. Now as far as the base is concerned, because it is a P type and it has to be forward biased here, you have to, maybe you can have an IB here, which is a microammeter, and then connect it to this, and you have to show the biasing. Because this is P, you have to take the lead from positive through body of some resistance R1 as before, and this will be going to positive and negative will go to the collector like this. Now on the other side, the output side here, what you have to do is you have to remember that emitter should be forward biased and our terminal of the battery should be only with respect to this N type of collector, because collector only has to be reverse biased. So for that, the collector has to take its lead from positive of the battery, negative, positive, negative, and this has to go to this N type through the body of a resistor R2, and then it has to go to this via some ammeter which measures IE in milliamperes, and this is microamperes, remember, in milliamperes, and that has to go to this. This is the connection. Now as far as the currents are concerned, because this is going from positive, IB will be like this, and because it is going towards the negative, conventional current to travel towards this negative, and therefore it is, because always on the emitter you have to mark the direction of the inside the transistor, you have to mark it on the emitter with the emitter being forward biased, because it is N type and it taking the lead from N of the battery, it is forward biased, so the electrons will go towards the base. In other words, conventional current will be going like this. In continuation with this will be my IE that's going here. So IE exits out of the transistor, IB is entering the transistor. Now if you have some crude analysis for at least remembering, with respect to this it may be negative, and therefore the electrons will be coming out. The electrons outside the battery, it has to go towards this. So yeah, this will be the direction in which the electrons are moving, but this will be the direction in which IC will come, because conventional current is always anti-parallel to the electron motion. So IC will be like this, IB is also like this, and IE is like this. So on looking at this, I understand IB is entering the transistor and IC is also entering the transistor, IE is exiting the transistor. Therefore, your validity is IB plus IC equal to IE, and that is still valid. To mark the positive and negative on the ammeter here, because this is positive and current flows like this will be the positive and this will be the negative. And here, because current is going like this will be the positive and this will be the negative. And what is measured here will be my VBC, will be the one that is measured between base to collector. and what is measured here will be my collector to emitter, VCE. This will be my VCE. That is all the circuit for this. This does not find much of application, so it's better you just know the circuit. But while drawing the circuit, you remember these are the things that you should finally learn that. Always current should be from the positive of the whichever biasing battery you have on either side, input as well as the output side. And collector being the common terminal in the common collector mode, that should be grounded here. That should be grounded here. And then because the base has to be forward biased, you connect the positive to the base, P type of base. And because the emitter also has to be forward biased, it has to take its lead from the negative of the battery at the other side. And as far as the collector goes, it has to be heavily reverse biased. The N type of collector should take its lead from the positive, only then it will be reverse biased. So much for this circuit. Here, because the current is going like this, IB will be into the transistor, and IC also, the electrons will, conventional current will flow towards the negative, no doubt, but here there is a positive. Therefore, that will push the conventional current in the upward direction. Because this is much more than this, predominantly the algebraic sum of these two currents will lead IC with a positive, with an upward sign like this. Actually, the current has to go downwards and go here, remember. But because there is a positive also that is coming along here, that will propel the conventional current in the upward, towards the transistor direction. This will move it away from the transistor direction. But because of the thanks to the reverse bias that this provides, the net current here, IC will be in this, as if it is going towards that. So IC is entering the transistor, IB is also entering the transistor, and IE is exiting the transistor, so that this equation still becomes valid. It is enough if you know this much as far as the transistor in the common collector mode is concerned. Our next study will be on the two types of current gains. The two types of current gains that you can think of. Now let us find out who is providing the forward bias for the input side and which is providing the reverse bias for the output collector side. That is our next question before we pass on to alpha and beta. Because if you know these foundations that you studied from under the three different modes, it will be easier to understand qualitatively as well as quantitatively the significance of alpha and beta gains. Now in the case of common base that you see, base is going to be the common one. Here you have the emitter and here you have the collector. So the base is going to be provided by, this is going to be provided, the base is going to provide this. So your IE will be my input. Of the IE that is coming along, my negligible fraction of the order of microamperes may go like this, much will go as IC. In this case, IC is the output. Always IC will be the output. Whether it is providing the input from the base or from the emitter, that should be distinctly known in the different modes, according to which your input current will be known. Here, the input current in the common base mode I am talking about, common base mode of NPN transistor. In the input current, the input current in the NPN transistor, it will be always away from the base because electrons will be propelled forward for the forward biasing, and therefore conventional current IE will be from base to emitter as shown here. And so this is the direction, sorry like this, and this will be here, and now this is the direction of the current here, and IC will have to come to this like this, and base also will have to drive current like this, so that this IB that comes at the base and IC that comes at the collector end, both of them will go into the transistor, whereas IE will emit out of the transistor. So that this relation of IE being equal to IC plus IB holds good. Now input current is equal to IE. Output current is equal to IC as usual. Now we are in electronics, we are not interested in the absolute value of IC and IE. We are only interested in the change that is brought about. The change, any change in one divided by the corresponding change in the other. And always output by input is what you study in terms of gain. Even in a simple machine, we see only the output energy by input energy. Likewise, you see, when you want to study current gain, you have to see the ratio of output current by input current, but more rather it is the ratio of a small change in output current to any change in the input current. That will be my gain. So alpha current gain will be equal to delta IC output current by delta IE for the input current. Here I am going to keep in the common base VBE is going to be a constant. So for a common VBE or VBC, this one between base to collector, if you keep that a constant, and for the constant, if you are going to somehow increase your IC, increase your IE, what is the change you get in IC? The ratio of delta IC by delta IE will give me the current gain. Just a second. Yeah, it will be my alpha. And now since delta IC is nearly equal to IE, I told you when I explained the action of the transistor, and delta IC is nearly equal to delta IE, point number 1. But IC is less than IE, definitely, because this is only output, it cannot exceed IE. Of the fraction of IE, some goes as IB and only the balance goes to IC. So delta IC will be less than, slightly less than delta IE. Therefore, delta IC by delta IE will be nearly equal to 1 but less than 1. Or in other words, alpha will take values of 0.95, 0.98, 0.95, 0.98, 0.99, etc. So it will take only values nearing 1 but definitely less than 1. It cannot exceed 1. So the ratio alpha will be of this order. Now coming to the next beta, current gain beta. Here, so this is the current gain is the ratio of change in collector current to the change in emitter current in the common base mode, common base current gain. That's called as common base current amplification or common base current gain, which is ratio of delta IC by delta IE for a common VBC, VCB or VBC. Now coming to beta, in beta we only think about the common emitter gain. Now common emitter gain will be like this, emitter will be coming like this and collector will be going here. This is emitter and this is base. Base is P type, emitter is N, collector is N as well. Now you have to connect. Now here this is going to be my, because if this is P, you will be connecting to a positive source, only then it will be forward biasing. So this will be the direction of IB. And then in the emitter side, VBE, because this is going to be connected to the negative, again electrons will flow like this. So the conventional current will be like this in the emitter, in the NPN transistor. Now the reverse bias, you are going to apply reverse bias for the collector. That means N has to take its lead from positive of the battery. That means conventional current will have to be like this, or in other words, into the transistor. So your IB and IC will go, this will be my IC. IB and IC will enter the transistor and IE will exit the transistor, so that IE is equal to IB plus IC. That is again valid. Now if you analyze what is the input current that is forward biasing the input side, it is only IB. Therefore, IB will serve as the input current in the common mode, common emitter mode. And IC is anyway the output current. In any of the modes, output current is going to be IC. Now, beta, the current gain in the common emitter mode, that's called as beta. The current gain called into play in the common emitter mode is beta, is given by delta IC by delta IB. That is beta. Now we know IE equal to IC plus IB. So for small changes, delta IE equal to delta IC plus delta IB. Now if you analyze this particular equation, we know delta IB is very much greater than IC is very much greater than delta IB, because this is of the order of milliamps and this is of the order of microamps. So this is delta IC will be very much greater. So the ratio of delta IC by delta IB will be delta IC by delta IB will be very much greater than 1. So beta will be of the order of 50 or 100 or 200, etc. depending upon what is the function we want it to serve. So the current gain beta is nothing but the current gain in the common emitter mode of the transistor, or in other words, it is the ratio of the change in collector current to the any change corresponding change in the base current. So delta IC by delta IB will be that, and that is given by beta, which is very large, namely of the order of 50, 100, 200, etc. This is what you should know. Delta IC is of the order of milliamps. Delta IE is also of the order of milliamps. And delta IB will be of the order of microamps. And delta IC will be nearly equal to delta IE, but still, however, delta IC will be less than delta IE. These are some small things that you should know. So beta will be of the order of so high a value. Alpha will be of the order of nearly 1, but close to 1, not exceeding 1. Say 0.95, 0.98, 0.99 and so on. Now what is the relation between alpha and beta? What is the relation between alpha and beta will be our next question. Now we know IE equal to IB plus IC. For small changes, delta IE equal to delta IB plus delta IC. Now dividing throughout by delta IC, delta IE by delta IC equal to delta IB by delta IC plus delta IC by delta IC. The delta IC will cancel here and leaving a factor of 1 there. Delta IC by delta IE is alpha. So delta IE by delta IC will be 1 by alpha. Similarly, delta IC by delta IB will be beta, and delta IB by delta IC will be 1 by beta plus 1. That implies, therefore, you have, now that we have understood what is the input current and so on, now we will have to transform this equation, and therefore 1 by alpha equal to, taking the LCM on the right hand side, it is 1 plus beta by beta. Or taking reciprocals, alpha will be equal to beta by 1 plus beta. From transforming this equation itself, we can have beta on the left hand side and alpha on the right hand side, which I am going to show you. This is equation 1, interrelating alpha and beta. In case you are given beta in a problem and you have to find out alpha, you make use of this equation. Now if you cross multiply, beta will be equal to alpha plus alpha beta. Now I want beta on this side, so I bring alpha beta to the side. So beta times 1 minus alpha equal to alpha. So beta will be equal to alpha by 1 minus alpha. This is the second equation. Beta will be equal. If you are given alpha and you have to find out beta, you make use of this equation. Now, the same derivation can be done using the fundamental relation like this. So delta IE equal to delta IB plus delta IC is what we saw. Now you divide throughout by delta IC. So delta IC by delta IE by delta IC equal to delta IB by delta IC plus delta IC by delta IC. As usual, this will become 1. This will become 1 by alpha equal to 1 by beta plus 1. Now, if you want to retain 1 by beta on one side, you bring the 1 to this side. So 1 by alpha minus 1 will be 1 by beta. Or in other words, 1 minus alpha by alpha equal to 1 by beta. Or beta will be equal to alpha by 1 minus alpha. Either way, you get this is the relation. So if beta is given and alpha has to be determined, you use the relation beta by 1 plus beta is nothing but alpha. If your problem gives you a data by which alpha is readily known, but beta is what you have to find out, then alpha by 1 minus alpha will be my beta. So this is the interrelation between alpha and beta. So knowing any one of them by some data given in the problem, you can find out the other. The next is the characteristic study. The characteristic study means as you change the voltage, you have got, as I told you, any transistor will have the input side as well as the output side, and you have the forward biasing on the input side and you have the reverse biasing on the output side. At the same, and you can have the output voltage regulated as per your desire, and similarly you can have the input voltage as per your desire. If you want to measure the output voltage, you have to connect a voltmeter in parallel in that side, and if you want to measure the current, either IB or IC or IE, you have to introduce an ammeter in series with that part of the circuit wherever it is desired. You have to take care that if it is IB that I want to measure and I place my ammeter in the path of IB, I have to place a microammeter there, not a milliammeter. If it is a current at the collector side, I can use a milliammeter. For measuring any IE, I can use a milliammeter. Now I am going to use only NPN transistor as originally told, point number 1, and with the preferably we use only common emitter as the emitter in mode for the study of characteristics. Characteristic study is the relation between voltage and current. As you regulate the voltage, how does current vary? When you change the voltage, accordingly everywhere, because the whole thing is interlinked, VCE and other things are all interlinked, all of them will be changing. So you have to somehow fine tune it so that that VCE is kept a constant, and the collector side the voltage is kept a constant, and you gently tune this so that for you have different values of VBE. Accordingly you have to find out what is the change in IB for the different values of VCE. So the circuit will be like this. It is a common emitter. So you have a base here as originally told, and you have an emitter here and a collector here. And this will be N, this will be P, and this will be N. Right. Now how are you going to give the biasing? The biasing should be such that there is a potential divider at the input as well as the output side, because the main object of the circuit is only to study the characteristics, whereby my voltage should be regulatable on the input side as well as the output side. Accordingly, let the current change in a way it should according to the principles of electronics. I don't bother. But what I regulate from my side is only the voltage. at the output as well as the input side. So I require a potential divider. Now, suppose the the P type of base has to take its lead from positive at the input side so as to forward bias it. So I will have a positive here and a negative here. And then I have to arrange a rheostat like thing. So that this is negative and this is most positive and this is most negative. So this is most positive and this is most negative. And I will have to take a tapping point or a sliding point or a jockey point of the rheostat. So that depending upon where I place this, its positiveness with respect to this will be changing. Thereby I am changing or regulating the forward bias voltage. Now this has to go to the base. Before it goes to the base, it has to go via some instrument which can measure my IB, because it's going to the base. So I will put my microammeter here, which is good enough to measure my IB. And the other end will go to the base as required. I also require a voltmeter to measure the voltage that may come across this, that may appear across this. So I introduce a voltmeter here, which will measure VBE, base to emitter voltage. And this will be like this, connected like this. So hope I have made myself clear. Because the P type of the base is of a P type semiconductor and it has to be forward biased on the input side, I have to take the lead from the more positive, relatively more positive compared to the other end. This is the other end which goes to the emitter, and this is the end which is going to the base. So the voltage that appears across this section of the entire rheostat is what is going to be fed as input voltage or VBE voltage. And why has this to be positive is our next question. Only then the P will take its lead from the positive end. Compared to this is negative, this is more positive compared to this. It may be less positive compared to the other extreme, but with respect to the other end of which is leading to emitter, this is more positive. So that positive should go to it, and via it has to go a micrometer which can measure my IB. And in between base and emitter, what voltmeter will measure is called as VBE, base to emitter voltage. Now you can put your plus, because this is current is going to be into the transistor, this will be plus and this will be minus. And because this is positive end, that which is in contact with the positive end will be positive and the other end will be, because this is the negative end of the entire rheostat and that is coming here, and so this will be the negative end. Now coming to the output side, because it is the N type of collector, it has to take its lead from positive of the voltage source at the collector emitter junction. So I have to take a positive here and negative here, positive here and negative here. Remember that the number of batteries here should be at least one more than the number of batteries in this section. And this has to be taken as a potential divider arrangement. You can take it like this, such that both of them are leading to common terminal here, and here you have the tapping point. This tapping point will be now fed to the N type of collector via an ammeter which can measure my IC, which is milliampere, and IC will be measured milliampere here, and that will be connected like this. And what is measured here between this end and that end, or here also you can take, this will be my VCE. Because the potential drop across the milliammeter will be negligibly small, because it's only in milliamperes, and compared to volts it will be some millivolts which we can ignore. So it doesn't really matter whether you place your VCE here or here, it doesn't really matter, and this is VCE. Because this is positive, this will be positive, this will be negative, and because this is positive with respect to this, so this will be the positive of milliammeter and this will be the negative of milliammeter. So after the long sight, you find that this is what will be happening. Now as you slide this along to different positions of the jockey, you find that the voltage will change, and IB will also change. And similarly, and you have to take care that you tune this time and again so that VCE is kept a constant. For a constant VCE, you slowly tune this so that VBE changes from its 0 value, and then slowly when you do that, your IB will also increase, and you have to draw a graph between VBE versus IB, keeping VCE a constant. So your graph will have, in electronic circuit graphs relating to electronic circuits, always you have the current on the y-axis, unlike electrical circuits. As I told you as was told in the semiconductor devices section, same way in transistor also, you will have your VBE here and IB here. So as you change your VBE, your IB will also change like this. For one VCE. For another VCE, this is V1 CE, V2 CE, like that. Now comes the question. This is for one VCE constant value. This is for another VCE constant value. You have a family of curves. Now what will be the VCE here? Now here you find that this will be for VCE equal to say 10 volts, and the first one will be for VCE equal to 4 volts. VCE equal to say 4 volts. The next one is for 10 volts. So for the lower one is corresponding to greater VCE, and the upper one is corresponding to a lesser VCE. It's quite understandable. If this constant value is kept increased, that means you are more heavily reverse biasing the collector. That means it will have more IC. Yeah, that means IC plus IB will be equal to IE. So the greater the IC means lesser will be my IB, and therefore for a greater VCE that it is, I find that this will come down. IB will come down. So this is for greater will be, the Y coordinate will be greater, and here the Y coordinate will be lesser. This is how you get. And you can take a small region which is almost linear and find out delta VBE by delta IB. That will be my RI input resistance is delta VBE, input impedance we call it, by delta IB. For a constant VCE constant. Collector to emitter, not common emitter. It's common emitter no doubt, but this is VCE refers to collector to emitter voltage. For a constant of that, delta VB by delta IB will be a constant. So much for the input side. The same circuit can be cast, I am finishing the session now. The same can be cast, and we can go to discuss how do you study the output characteristics. This is the input characteristic and this is the input impedance. And for the output characteristics, we will continue in our next session. Thank you.